Hello, in this lecture we will find out the area of the orange shape using two different methods. In the drawing we have square ABCD. One side of square ABCD equals to 10 units. Inside square ABCD we have two semicircles that intersect with each other. Semicircle APD and semicircle CPD intersects with each other and create the blue lens. A lens is the common area that was created by the intersection of the two semicircles with each other. So this blue lens is the common area of the two semicircles, and we also have a quarter circle ABQD that intersects with the semicircle CPD, and they create, by the intersection of the quarter circle with this semicircle, they create the big lens. And our mission is to find out the area of this orange shape. Okay, it is very easy to see from the drawing that the area of this orange shape equals to the area of the big lens minus the area of the blue lens. Again, the area of the big lens minus the area of the blue lens gives us exactly the area of this orange shape. So I'll write it down. The area that we are looking for is the area of the orange shape. And the area of the orange shape equals to the area of the big lens minus the area of the blue lens. Okay, and repeat again, the area of the big lens minus the area of the blue lens gives us the area of this orange shape, the area that we are looking for. So we'll use two methods in order to find out the area of this orange shape. In the first method, we'll develop, actually we know that the blue lens was created by the intersection of the two semicircles with each other. And it is very easy to see from the drawing that the two semicircles are perpendicular to each other. Okay, the two semicircles are perpendicular to each other, and so this the common area between the two semicircles, it is the blue lens. So, and we know that the two semicircles, semicircle CPD and semicircle APD, are perpendicular to each other. And actually the intersection of the quarter circle, this semicircle, created the common area here, that is the big lens. So, and we know that this quarter circle is perpendicular to this semicircle. Here they have angle of 90 degrees between them. So actually we know that both the blue lens and the big lens was created by two shapes that are perpendicular to each other. Therefore, we will draw two semicircles that are perpendicular to each other. Those two semicircles are perpendicular to each other. This angle equals 90 degrees. And the radii of each semicircle will be equal to A. This will be the radii of this semicircle, and B will be the radii of this semicircle. And we will find out the area of this lens, that is the common area of, and it is the common area of those two semicircles that intersect with each other. And after we find out the formula for this lens, we'll use that formula in order to find out the area of the blue lens, and then we'll use the same formula in order to find out the area of this big lens. Actually, okay, so this will be the second method, while in the first method, this will be the first method, while in the second method, we'll directly find out the area of the blue lens. We'll directly find out the area of this big lens. Then we'll subtract the two areas from each other, and this will give us the area of this orange shape. Okay, so but before we start to answer the question, I present to you two new concepts. The first concept is the area of a sector. The green shape is a sector, that is a portion of a circle, and the area of this green sector equals to the ratio between the angle that is between his legs, that is theta, over the angle of the whole circle, that is 360 degrees in terms of degrees, or 2 pi radians. So the ratio between theta and 2 pi, or theta and 300 degrees, if we want to talk in terms of degrees, it is theta over 360 degrees. If we want to talk in terms of radians, it is theta radians over 2 pi radians. So the ratio between those two angles will give us the relative percentage that this sector occupy out of the area of the entire circle, and when we will multiply the relative percentage by the area of the entire circle, that is to say pi r square, it will give us exactly the area of this sector. So repeat again that the area of this sector, if we want to talk in terms of radians, and in this lecture we'll talk in terms of radians, not in terms of degrees, it is theta degrees over 2 pi degrees. That gives us the relative percentage that this sector occupy out of the area of the entire circle, and then we will multiply the relative percentage by the area of the entire circle, that is pi r square, and this will give us the area of this sector, the area of this green sector. Okay? The second concept that I want to clarify is the area of this circular segment, the green circular segment AB. Okay? The area of this circular segment AB equals to the area of sector AOB, the area of this sector, minus the area of triangle AOB. Again, the area of sector AOB minus the area of triangle AOB will give us exactly the area of this circular segment AB. Okay, it is very easy to see from the drawing that if you subtract the area of triangle AOB from the area of sector AOB, we get exactly the area of this circular segment AB. Okay, so we start in the first method. So in the first method, we will build a general formula for the area of this lens that was created by two semicircles that are perpendicular to each other, and we'll use the new formula in order to find out the area of this blue lens that was created by two semicircles that are perpendicular to each other, and then we'll use the same formula in order to find out the area of the big lens, and the big lens was created by the quarter circle that is also perpendicular with this semicircle. Okay, so both the blue lens and the big lens also were created by two shapes that are perpendicular to each other. Therefore, we can take those two semicircles that are perpendicular to each other, and by creating a formula for the length of this lens, that could be either the blue lens or the big lens. So therefore we can use the new formula in order to find out the area of this blue lens, and then in order to find out the area of this big lens. Why? Because those two semicircles are perpendicular to each other, exactly like the two semicircles that are perpendicular here to each other that created the blue lens, and exactly like the quarter circle that is perpendicular to this semicircle, and the intersection of those two shapes created the big lens, and indeed the quarter circle perpendicular to this semicircle. Therefore we can use the same formula in order to find out the area of the big lens also. Okay? So here we will define the centers of the two semicircles, SO. O is the center of this semicircle. Here M is the center of this semicircle. This is point N. This is point L. Here point O is the center of this semicircle. Point N is the point on this semicircle itself. This is exactly the definition of a radius. That is to say, ON is the radius of this semicircle, and we define the radius of this semicircle as A. That is to say, the radius of this semicircle equals to A units in its length, and here we have point M is the center of this semicircle. Point N is the point on this semicircle itself. Therefore, MN is the radius of this semicircle, and we will define the radius of this semicircle as B. Here, point M is the center of this semicircle, point L is the point on this semicircle itself, therefore ML is also the radius of this semicircle, that is equal to B according to our definition. Likewise, point O is the center of this semicircle. Point L is the point on this semicircle itself, that is to say OL is the radius of this semicircle, that is equal to A units according to our definition. As I've already mentioned, here in the original drawing, the two semicircles perpendicular to each other, and also the two semicircles will be perpendicular to each other. So this angle equals to 90 degrees. I repeat again that the same thing is true to the quarter circle that is perpendicular to this semicircle. So actually the two lenses, the blue lens and the big lens, were both created by two shapes that are perpendicular to each other. Therefore, because of the fact that those two semicircles are perpendicular to each other, so we will develop the formula that will produce the area of the big lens, and we can derive from the formula that we will create the area of the blue lens. Why? Because the blue lens and the big lens were created by two shapes that are perpendicular to each other, and because of the fact that those two semicircles are also perpendicular to each other, we can derive the areas of the blue lens and the area of the big lens from the formula that we will develop for the area of this lens. So the area of this lens could be the area of the big lens and also the area of the blue lens. Okay? So here we have, actually we draw the radius ML in such a way that is perpendicular, that is tangent to this semicircle. The radius ML is tangent to this semicircle, that is to say L is the point of tendency. Point of tendency of tangent ML with this semicircle. Okay? And here we have the radius OL of this semicircle that is drawn to the point of tendency. That is to say, it is drawn to point L, that is the point of tendency of tangent ML with this semicircle. And whenever we have a radius that is drawn to the point of tendency, then tangent ML will be perpendicular to the radius LO. So if ML is perpendicular to LO, it means that this angle equals to 90 degrees. According to the rule that the tangent to a circle is perpendicular to the radius drawn to its point of tendency. In the next step, we'll join points N and L together by a straight line. So by joining points N and L together by a straight line, we divided the length into two parts. So those are the two parts. So we will calculate the area of each part. We'll add the two areas together, and this will be the area of this length that could be either the blue length or the big length. So we'll use the new formula in order to find out the big length, the area of the big length and the area of the blue length. Here we will join points M and O together by a straight line. As I already mentioned, the straight line NL divides this length into two parts. We have the first part is the upper circular segment of this length. So what is the area of this upper circular segment, the green shape of this length? Here, the area of the upper circular segment of this length, the green shape, it's actually the upper circular segment of the length. So what is the area of the upper circular segment of this length? It is very easy to see from the drawing that it is equal to sector NOL, the area of sector NOL minus the area of triangle NOL. Okay, so it is equal to the area of sector NOL this is sector NOL that I copied from the original drawing minus the area of triangle NOL. Okay. Side NO equals to A units. Side OL equals also to A units in its length. Here we will define angle NOM as theta. The right triangle NOM is congruent to the right triangle OML. That is to say, those two triangles can go into each other according to side rule. I'll explain what I mean. First of all, those two sides, they are both equal to A units, therefore they are equal to each other. In addition, those two sides, they are both equal to B, therefore they are equal to each other. And finally, side OM is a common side that belongs to both triangles, so side OM equals to itself. In conclusion, found out that all three sides of triangle NOL can go into all three sides of triangle MOL, therefore those two triangles can go into each other according to side rule. And from the fact that those two triangles can go into each other, we will conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Okay? Those two triangles can go into each other, therefore the corresponding angles must be also equal to each other. That is to say that if this angle equals to theta, then this angle must be also equal to theta because of the fact that those two angles are equal to each other. So in conclusion, I found out that angle NOL, the angle between the legs of sector NOL, it is equal to theta plus theta, that is 2 theta. And I've already presented to you the area of a sector. How to find out the area of the sector? It is equal to 2 theta radians over 2 pi radians. So the ratio between the two angles gives us the relative percentage that this sector occupy out of the area of the entire circle. And then when we will multiply the relative percentage by the area of the entire circle, that is pi r square, and r equals to a, so it is pi a square, it will give us exactly the area of this sector NOL. Okay? So this is the area of sector NOL. We have pi in the numerator and pi in the denominator, so pi will get cancelled. We have 2 in the numerator and 2 in the denominator, so 2 also will get cancelled. In conclusion, we found out that the area of this sector NOL equals to theta times a square. And in order to find out the area of this circular segment NL, we have to subtract from the area of this sector the area of triangle NOL. So here, this is triangle NOL. We will find out the area of triangle NOL later. So this is the area of the circular segment NL. The area of sector NOL, that is theta times a square, minus the area of triangle NOL. Okay? So in the next step, we'll find out the area of the lower circular segment of this length. We find out the area of this orange shape that is defined as the lower circular segment NL. So what is the area of the lower circular segment NL? The area of the lower circular segment NL the area of this orange shape it is very easy to see from the drawing that the area of this lower circular segment NN, the orange shape, equals to the area of sector NLM minus the area of triangle NLM. Again, the area of sector NLM minus the area of triangle NLM will give us exactly the area of this lower circular segment NN. Okay, so I write it down. The area of sector NML, the area of this sector this is sector NML, the area of this sector minus the area of triangle NML equals to the area of this circular segment NL. It's very easy to see from the drawing that if you subtract the area of triangle NML from the area of sector NML, we get exactly the area of this sector, circular segment NL. So what is the area of sector NML? Sector NML. First of all, we have to find out angle NML, the angle between the legs of this sector. Here, this angle equals to theta, this angle equals to, it is 90 degrees, but in terms of radians, is pi over 2 radians. So, the missing angle must be equal to 90 degrees minus theta in terms of degrees, or it is pi over 2 minus theta in terms of radians. Because of the fact that pi over 2 radians equals to 90 degrees. So it is pi over 2 minus theta radians. The same thing is true in triangle MOL. This angle equals to theta, this angle equals to 90 degrees, so this angle 90 degrees or pi over 2 in terms of radians, so this angle must be equal to pi over 2 minus theta radians. In order to complete the sum of the angles to 180 degrees, this angle must be equal to pi over 2 minus theta. So we'll add the two angles together, and this will give us the size of the angle NML. Pi over 2 minus theta plus pi over 2 minus theta. Here equals to pi over 2 plus pi over 2 is pi. And minus theta plus minus theta is minus 2 theta. So in conclusion, we found out that the size of this angle NML equals to pi minus 2 theta. Here, in this step, our mission is to find out the area of this length that could be any length. Okay? So here, that could be either the blue lens or the big lens. Okay? So, what is the area of sector NML? The area of sector NML equals to, here it is pi minus 2 theta, angle NML equals to pi minus 2 theta radians. So the area of sector NML equals to pi minus 2 theta over 2 pi times the area of this circle, that is pi r square, and here r equals to b, so it is pi b square. This is the area of circle NML. We have theta in the numerator and theta in the denominator, so theta will get cancelled. In the next step, we will open the brackets here and we will get that this is pi b square over 2. And here we have minus 2 theta over 2 times b square. So here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. So in conclusion, we found out that the area of this sector NML equals to pi b square over 2 minus theta b square. And we have to subtract from the area of this sector the area of triangle NML. So it is minus the area of this triangle NML. This is equal to the area of the lower circular segment NL. So it is minus the area of triangle NML. And we of course have to add the two areas together in order to find out the area of this lens. Again, we have to add the two areas together. The upper circular segment to the lower circular segment. That will give us the area of this lens. The area of this lens, that could be the blue lens or the big lens. And also other lenses that were created by the intersection of two shapes that are perpendicular to each other, exactly like in our drawing. Exactly like in our drawing, that the blue lens is created by the two semicircles that are perpendicular to each other, while the big lens were created by the intersection of the quarter circle, this quarter circle with this semicircle. They are also perpendicular to each other. So we will add the areas of those two circular segments with each other, and this will give us the area of this lens. So the area of this lens This is the sign for the area. The bracket here is the sign for the area. For the area of this length equals to the area of the upper circular segment plus the area of the lower circular segment. And we already found out that the area of the upper circular segment, the green shape, equals to the area of sector NOL this is sector NOL minus the area of triangle NOL. This is the area of the upper circular segment, the orange shape, so this is, and plus the area of the lower circular segment. So the area of the lower circular segment equals to the area of sector NML this is sector NML minus the area of triangle NML. Okay, this is the area of the lower circular segment NL. So the sum of those two areas gives us the area of this length. So here we have to add the two sectors together. So it is equal to the sum of the areas of the two sectors, that is actually sector NOL this is sector NOL plus sector NML. This is sector NML. Okay, we have to add two sectors together, and we have the negative sign before this, the area of the triangle. We have also the negative sign before the area of this triangle, so we have to subtract the sum of the areas of those two triangles. So it is minus the sum of the areas of the two right triangles. It says minus the sum of the areas of triangle NOL plus the area of triangle NML. Okay, we have to add the areas of two sectors together and then to subtract from it the sum of the areas of those two triangles. But we already found out that the area of sector NOL equals to theta A square, while the area of sector NML equals to pi B square over 2 minus theta B square. So this expression equals to the sum of the areas of those two sectors minus the area minus the sum of the areas of those two triangles. So we have to find out the area of those two triangles. In order to find out the area, the sum of the areas of those two triangles, we combine them together. In this way we get quadrilateral. So here we have quadrilateral NMOL that was created by the combination of the two triangles together. We will join points N and O together by a straight line. This angle equals to 90 degrees, it is a right angle. This angle also equals to 90 degrees, it is also a right angle. NO equals to A, NM equals to B, NL equals to B, and OL equals to A. So here we created two right triangles, and it is very easy to calculate the area of the right triangles. We have the green right triangle O and N, and we have the right triangle OML. So we calculate the areas of each right triangle. So the area of the green right triangle O and M equals to the base of the triangle that is B times the height to the base that is A over 2. While the area of the orange right triangle OML equals to the base of the triangle that is A times the height to the base that is B over 2. Okay, BA and AB is the same, so we'll add the two expressions together and we get that BA plus AB is 2AB, so it is 2AB over 2. We have 2 in the numerator and 2 in the denominator, so in conclusion, we found out that the sum of the areas of those two right triangles, it is equal to A times B. Okay, it is equal to A times B. Therefore, the area of this length equals to this expression that is the sum of the areas of the two sectors minus the sum of the areas of those two triangles, that is actually A times B. Okay, so actually I found out that the area of the length that we are looking for is equal to the area of the length equals to the sum of the areas of the two sectors, that is actually theta times A squared plus pi B squared over 2 minus theta times B squared. This is the sum of the areas of the two sectors minus the sum of the areas of the two triangles, that is AB, so it is minus AB. So here we take theta as a common factor out of those two expressions. So here we took theta as a common factor, so what is left from this expression after we took from it theta as a common factor? What is left is actually A squared. And what is left from this expression after we took from it theta as a common factor? What is left is actually minus B squared. So it is, we have also to add pi B squared over 2. And we have to subtract from it AB. So that is actually the area of this length. This expression equals to the area of the length. But we want to eliminate theta here because we want to have a formula that the only missing variable will be A and B. I will remind to you that A is the radius of this semicircle, while B is the radius of the other semicircle. So A and B are the radii of the two shapes. So now, in order to eliminate theta, I will copy the right triangle NOM that consists angle theta, and we will try to eliminate theta by this right triangle, triangle NOM. So here in this right triangle, triangle NOM, we know that tangent theta equals to NM over NO. Tangent theta equals to NM over NO. NM equals to B and NO equals to A. So in conclusion, we found out that tangent theta equals to B over A. Now we want the value of theta itself. In order to get the value of theta itself, we'll operate the opposite function of tangents, that is tangents minus 1, on the results, that is B over A. This operation will give us the value of theta itself. So here we get that the value of angle theta itself equals to tangents minus 1, that is the opposite function of tangents, of B over A. We actually found out the value of theta itself. Now we can substitute theta by tangents minus 1 of B over A. In this way, we actually created a formula for the area of this lens, that the only missing variables in this formula will be A and B, that are the radii of the two shapes that intersect with each other at 90 degrees. So now we'll substitute theta by tangents minus 1 of B over A, and we get that the area of the lens that we are looking for equals to theta. We have already found out that theta equals to tangents minus 1 of B over A times A square minus B square plus pi B square over 2 minus AB. So we found out a formula that is the area of a lens, and for our use, the area of a lens could be the area of the blue lens and the area of the big lens also. Okay. Here it could be the area of the blue lens and also the area of the big lens. So first of all, We'll use this formula in order to find out the area of the big lens. Okay, so the area of the big lens this big lens was created by the intersection of the quarter circle with this semicircle. I repeat again, the big lens was created by the intersection of the quarter circle with this semicircle. And the radius of the quarter circle is equal to 10 units, that is to say A equals to 10, while the radius of this semicircle that intersects with the quarter circle, here we know that the diameter of the semicircle equals to 10 units. It is given as the question. Therefore the radius must be equal to 5. So B equals to 5. So here we know that A equals to 10, B equals to 5, so we'll put the values of A and B in the formula, and this will give us the area of this big lens. So we'll get here that the area of the big lens equals to tangents minus 1, B is 5, A is 10, and 5 over 10 is 1/2, that is 0.5, times A square. A is 10, so A square is 10 square, minus B square. B is 5, so B square is 5 square, plus pi times B square. B is 5, so B square is 5 square, over 2, minus A is 10 and B is 5, so it is minus 10 times 5. So the area of the big lens will be equal to tangents minus 1 of 0.5 times 10 square. 10 square is 100, minus 5 square. 5 square is 25. 100 minus 25 is 75. So it is 75 times tangents minus 1 of 0.5 plus 5 square is 25. 25 over 2 is 12.5. So in conclusion, this expression equals to 12.5 pi. Minus 10 times 5 is minus 50. So in conclusion, we found out that the area of the big lens equals to 75 times tangents minus 1 of 0.5 plus 12.5 pi minus 50. Okay. In the next step, we'll find out the area of the blue lens. The area of this blue lens, it is very easy to see from the drawing that the blue lens was created by intersection of those two semicircles with each other. The common area is the blue lens. The common area of those two semicircles that intersect with each other created the blue lens. And we know that the radius of each semicircle equals to 5 units. That is to say, A equals to 5. Here, A equals to 5. And B also equals to 5 units. So we'll put the value of A and B inside the formula of the lens, and we'll find out the area of this blue lens. So the area of the blue lens will be equal to tangent minus 1 of b over a. b is 5 and a is 5. 5 over 5 is 1. So it is tangent minus 1 times a square. A is 5, so a square is 5 square. Minus b square. B is also 5, so b square is 5 square also. 5 square minus 5 square is 0, so this expression will be equal to 0. And we also have to add to this expression pi b square. B is 5, so b square is 25. And 25 over 2 is 12.5. In conclusion, this expression pi b square over 2 equals to 12.5 pi minus ab. A is 5, b is 5, so a times b is 5 times 5, that is 25. So actually, this expression equals to 0, so in conclusion, we found out that the area of the big lens, the area of the blue lens, of course, the area of the blue lens equals to 12.5 pi minus 25 square units. Okay. Now we subtract the two areas from each other, and this will give us the area of the green shape. Very simple. The area of the orange shape. The area of this orange shape equals to the area of the big lens minus the area of the blue lens. So I write it down. The area of the orange shape is equal to the area of the big lens minus the area of the blue lens. Okay? And we have already found out that the area of the big lens equals to 75 times tangent minus 1 of 0.5 plus 12.5 pi minus 50. This is the area of the big lens, and we have to subtract from it the area of the blue lens. And we have already found out that the area of the blue lens equals to 12.5 pi minus 25. 12.5 pi minus 25, yes. Here we will open the brackets, and we will get that the area of the orange shape equals to 75 times tangent minus 1 of 0.5 plus 12.5 pi minus 50. Here we will open the brackets, so here it will be equal to minus 12.5 pi, and we have here minus with minus is plus, so it is minus 25, it is plus 25. So in conclusion, we found out that the area of the big lens equals to, here we have 12.5 pi minus 12.5 pi is 0. And we have here minus 50 plus 25 equals to minus 25. In conclusion, we found out that the area of the orange shape equals to 75 times tangents minus 1 of 0.5 minus 25. Okay, and we know that tangents minus 1 of 0.5 equals to 0.4636. Okay, this is the value of tangents minus 1 of 0.5. So we'll substitute tangents minus 1 of 0.5 by 0.4636, and we'll get that it's 75, and tangents minus 1 of 0.5 is 0.4636 minus 25. Here 75 times 0.4636 is 34.77 minus 25, and 44.77 minus 25 is 9.77. So we actually found out that the area of the orange shape that we are looking for equals to 9.77 square units. Okay. Here, the area of this green shape and the area of this orange shape, dpq, equals to 9.77 square units. We finished in the first method. In the next step, I will present to you how to find out the area of this orange shape according to the second method. In the second method, we will calculate directly the area of the blue shape. We'll calculate directly the area of this blue lens. We'll calculate directly the area of this big lens, and we'll subtract the two areas from each other, and this will give us the area of this orange shape. Okay. So here we know that we start from calculating directly the area of this blue shape. We know that this blue shape was created by the intersection of those two semicircles with each other. So here I copied the two semicircles, and they intersect with each other at 90 degrees, of course. So this angle equals to 90 degrees. And here we can use the drawing from the first method. If we define A as 5 and B also equals to 5, this will give us exactly those two semicircles, because we know that the radius of each semicircle equals to 5 units. So if here A equals to 5 and B equals to 5, this shape is exactly the blue shape. Okay? Here point O is the center of this semicircle, point N is the point of the semicircle itself, that is to say ON is the radius of this semicircle, that is equal to 5 units. This is giving us the equation that the radius of each semicircle equals to 5 units. Likewise, here M is the center of this semicircle. L is the point of this semicircle itself. That is to say, ML is the radius of this semicircle, that is equal also to 5 units. The same thing is true here. This is the radius of this semicircle, that is also equal to 5 units. And OL is the radius of this semicircle, that is equal also to 5 units. So because of the fact that those two semicircles are identical, so it means that if we draw this radius in such a way that it will be perpendicular to the diameter, so if we know that this angle equals to 90 degrees and this angle also equals to 90 degrees, because of the fact that those two semicircles are identical, then it means that the radius that is perpendicular to this the diameter of this semicircle, it will be also tangent to the other semicircle at point L. Okay, the same thing is true here. If we draw the radius ML in such a way that it will be perpendicular to the diameter, then it also will be tangent to the other semicircle at point L. Okay? So here we have 1, 2, 3 right angles, and we know that the sum of the angles in any quadrilateral is equal to 360 degrees, so this angle must be also equal to 90 degrees, and also according to rule number 1, we know that this radius, it is drawn to the point of tendency, that is to say, it is drawn to point L, that is the point of tangency of tangent ML with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent ML will be perpendicular to the radius OL. So we have two different reasons that this angle equals to 90 degrees. So actually we have here a square. In the next step, we join points N and O together by a straight line. So here, so our mission here is to find out the area of the blue lens. This is the blue lens, and you want to find out the area of this blue lens. Okay? So here we find out the area of this circular segment, the area, and here, because of the fact that those two semicircles are identical, they have the same radii, it means that those two circular segments will be also identical and will be with the same areas. That is to say, we can multiply the area of this circular segment by 2, and this will give us the area of the blue lens. Okay, so what is the area? What is the area of circular segment NL? The area of circular segment NL it is very easy to see from the drawing that the area of the circular segment NL, the green shape, equals to the area of sector NOL minus the area of triangle NOL. Again, the area of sector NOL minus the area of triangle NOL will give us exactly the area of the circular segment NL. It is the area of sector NOL This is sector NOL minus the area of triangle NOL. Triangle NOL is a right triangle with sides of 5 and 5. The legs of this sector each equals to 5 units, and this angle equals to 90 degrees. And because of the fact that this angle equals to 90 degrees, it means that this sector NOL is a quarter circle. And we know that the area of any quarter circle equals to the area of the circle over 4. The area of this circle is pi r squared, and r equals to 5, so it is pi 5 squared. This is the area of the circle. And if we divide it by 4, we will get the area of this sector. Pi 5 squared over 4 is the area of sector NOL, and the area of this triangle is the base times the height over 2. The base is 5, the height is 5 over 2. So we found out that the area of sector NL equals to pi times 5 squared over 4 minus 5 times 5 over 2. Okay. Now we have to multiply the area of this circular segment by 2 in order to get the area of the blue lens. You can see here that here if we calculate the area of the lower circular segment, it will give us exactly the same result. It will be equal to the area of sector NLM minus the area of triangle NML. And sector NML is equal to the area of sector NML equals to the area of sector NOL, and the area of triangle. So then we have to subtract the area of triangle NML, but the area of triangle NML is equal to the area of triangle NOL. So because of the fact that those two circular segments are identical, we will just multiply the area of this circular segment by 2, and this will give us the area of this blue lens. So the area of the blue lens this is the blue lens. Is 2 times the area of circular segment NL. So it is 2 times the area of circular segment NL, and the area of circular segment NL equals to pi times 5 square over 4 minus 5 times 5 over 2. 2 times the area of circular segment NL equals to the area of the blue lens. So here we'll open the bracket and we get that 2 times pi 5 square over 4 minus 5 times 5 is 25, so it is 25 times 2 over 2. So here we have to divide both the numerator and the denominator of this expression by 2. So here what is left in the numerator is pi. After we divide it by 2, it is pi times 5 squared, that is 25 pi, and 4 over 2 is 2. So this expression equals in total to 25 pi over 2, minus we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled and we left only with 25. So the area of the blue lens equals to 25 over 2 is 12.5. So this expression equals to 12.5 pi minus 25. Okay, so in conclusion, we found out that the area of the blue lens equals to 12.5 pi minus 25 square units. Okay. So we found out the area of the blue lens. In the next step, we'll find out the area of this big lens. And the area of the big lens, so the big lens itself was created by the intersection of the quarter circle with this semicircle. So here, the intersection of this quarter circle with this semicircle created the area of the big lens. So we'll find out the area of this big lens. Okay. So our mission is to find out the area of this big lens directly from the drawing without any formula. Note that the radius of the quarter circle is equal to 10 units. D A we define the center of this semicircle as point O. This is point L. Point O is the center of the semicircle. Point L is the point of the semicircle itself. Therefore, OL is the radius of the semicircle that is equal to 5 units. Point O is the center of the semicircle. Point D is the point on the semicircle itself. That is to say, line segment DO is the radius of this semicircle that is equal to 5 units. In the next step, we join the two centers together by a straight line. And here we note that the quarter circle is perpendicular to the semicircle. That is to say, this angle equals to 90 degrees. Here we join points A and L together by a straight line. L is the point of tangency of tangent OL with this quarter circle. Here point A is the center of the quarter circle. Point L is the point on the quarter itself. This is exactly the definition of a radius. That is to say, AL is the radius of this quarter circle that is equal to 10 units. So here we have the radius AL that is drawn to the point of tendency. That is to say, it is drawn to point L that is the point of tendency of tangent OL with this quarter circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OL will be perpendicular to the radius LA. So if OL is perpendicular to LA, it means that this angle equals to 90 degrees. So it is very easy to see from the drawing that those two triangles can go into each other according to side rule. I will explain what I mean. Here, those two sides, they are both equal to 10 units, therefore they are equal to each other. In addition, those two sides, DO and OL, they are both equal to each other, they are both equal to 5 units, therefore they are equal to each other. And finally, AO is a common side that belongs to both triangles, so it equals to itself. So, of course, that those two triangles can go into each other according to side rule. So if angle, therefore those two angles are equal to each other. According to the rule that corresponding angles in congruent triangles are equal to each other. So if this angle equals to theta, we know that those two angles are equal to each other. So this angle must be also equal to theta. Okay? In the next step, we join points D and L together by a straight line. By joining points D and L together by a straight line, we actually divided the big lens into two parts. So we will calculate the area of each part, we will add the two areas together, and this will give us the area of this big lens. Very simple. So here, in the first step, we calculate the area of the upper circular segment of the big lens. But before that, what is the size of this angle? This angle equals to theta. This angle equals to 90 degrees, that is pi over 2 in terms of radians. So the missing angle must be equal to pi over 2 minus theta in order to complete the sum of the angles in this right triangle to 180 degrees. This angle must be equal to pi over 2 minus theta. And the same thing is true in this right triangle. This angle equals to theta. This angle equals to 90 degrees, that is pi over 2 in terms of radians. So this angle must be equal to pi over 2 minus theta for the same reason. Okay. So here, what is the area of the upper circular segment DL? The area of the upper circular segment DL the area of the upper circular segment DL. It is very easy to see from the drawing that the area of the upper circular segment DL equals to the area of sector ADL minus the area of triangle ADL. The area of sector ADL minus the area of triangle ADL gives us exactly the area of the circular segment DL. So it is equal to the area of sector ADL This is sector ADL. The angle between the legs of sector ADL, it is equal to 2 theta minus the area of triangle ADL. Minus the area of triangle ADL. I repeat again, the area of circular segment ADL, this shape, is equal to the area of sector ADL minus the area of triangle ADL. The area of sector ADL equals to 2 theta equals to 2 theta over 2 pi times the area of this circle, that is pi r squared, that is pi is 10, so it is pi r squared, r is 10, so it is pi 10 squared. So the area of sector ADL equals to this expression. We have theta in the numerator and theta in the denominator. Theta will get cancelled. We have 2 in the numerator and 2 in the denominator, so 2 also will get cancelled. So in conclusion, found out that the area of sector ADL equals to 10 squared is 100 times theta, so it is 100 times theta. And we have to subtract from it the area of this triangle ADL. AL equals to 10, AD equals to 10. So the area of triangle ADL equals to the multiplication of the sides by each other, that is 10 times 10 times sinus the angle between the sides, that is 2 theta over 2. So in conclusion, we found out that the area of circular segment DL equals to 100 times theta minus 10 times 10 is 100, 100 over 2 is 50, times 50 times sinus 2 theta. Okay. Now our mission is to find out the value of theta and the value of sinus 2 theta. In order to find out the value of theta and sinus 2 theta, I will copy in a new page the right triangle AOD that contains angle theta, and we will derive the value of theta and the value of sinus 2 theta from this right triangle. So I will draw the right triangle ADO or AOD, this new page. So I copied the right triangle ADO in this new page, and here it's very easy to see that in triangle ADO, tangents theta equals to DO over DA. DO equals to 5, DA equals to 10, so it is 5 over 10, that is 0.5. In conclusion, we found out that tangents theta equals to 0.5. Now we will operate the opposite function of tangents on the result, and this will give us theta itself. So theta itself equals to tangents minus 1 of 0.5. Okay. We found out that theta equals to tangents minus 1 of 0.5. In the next step, we will find out the value of sinus 2 theta. So I copy the right triangle DOA again here. This is the right triangle, this angle equals to 90 degrees, of course. So I copied the right triangle ADO here. We'll implement the Pythagoras theorem on the right triangle ADO in order to find out the value of the hypotenuse. So by PT, the version of Pythagoras theorem, in the right triangle ADO, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the square of the hypotenuse is AO square, and it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to AD squared, that is 10 squared, that is 100, plus DO squared. DO is 5, so DO squared is 5 squared, that is 25. So in conclusion, we found out that AO squared equals to 125. We take a root out of this equation, and we get that AO equals to the square root of 125. But 125 is 25 times 5. We take a root out of this equation, and we get that the square root of 25 is 5, so inside the root we left only with 5. So in conclusion, we found out that the hypotenuse AO of the right triangle ADO equals to 5 times square root of 5. Okay? And we also know that sinus 2 theta equals to 2 sinus theta cosine theta. So sinus 2 theta equals to 2 times sinus theta. Here sinus theta equals to DO over AO. Sinus theta equals to DO, that is 5, over AO, that is 5 times square root of 5, times cosine theta. Cosine theta equals to dA over OA. dA is 10, OA is 5 times square root of 5. Okay, so here we have 5 in the numerator and 5 in the denominator, so 5 will get cancelled. So here we have in the numerator 2 times 10 over square root of 5 times square root of 5 is 5 times 5. Okay, so here 10 over 5 is 2. So in the numerator we have 2 times 2 over 5. 2 times 2 is 4 over 5. So in conclusion, we found out that sinus 2 theta equals to 4/5. Okay? Sinus 2 theta equals to 4/5. So I copy again the result that we got here. We found out that tangent minus 1 of 0.5 equals to theta, and we found out that sinus 2 theta equals to 4/5. Okay, and we've already found out that the area of the upper circular segment of the big lens DL it is equal to 100 times theta minus 50 times sinus 2 theta. I'll repeat again. The area of the upper circular segment DL of the big length equals to 100 times theta minus 50 times sinus 2 theta. Now we'll substitute theta by tangent minus 1 of 0.5, and we substitute sinus 2 theta by 4/5, and we get that the area of the upper circular segment of the big length DL, it is equal to 100 times theta, and theta is tangent minus 1 of 0.5 minus 50 times sinus 2 theta. And we already found out that sinus 2 theta equals to 4/5, so we substitute sinus 2 theta by 4/5, and we get that the area of the upper circular segment DL of the big length equals to 100 times tangent minus 1 of 0.5 minus, here we have 50 over 5 is 10, and 10 times 4 is minus 40. So in conclusion, we found out that the area of the upper circular segment of the big length equals to 100 times minus 1 of 0.5 minus 40 square units. In the next step, we'll find out the lower circular segment of the big length. Here we'll find out the value of this area. Okay. So we'll copy again. We have all the things here. I'll just copy them here in order to make it clear. We have to find out the size of this area, the lower circular segment DL of the big length. This again equals to 90 degrees. So actually the size of angle DOL, the size of this angle, it is equal to pi over 2 minus theta plus pi over 2 minus theta. This is actually pi minus 2 theta. So this angle equals to pi minus 2 theta. So what is the area of the lower circular segment DL? The area of the lower circular segment DL of this lower circular segment DL will be equal to the area of sector DOL minus the area of triangle DOL. Okay, so it is equal to the area of sector DOL This is sector DOL, and we have to subtract from it the area of triangle DOL. This is triangle DOL. So the area of sector DOM will be equal to pi minus 2 theta over 2 pi times the area of the circle that is pi r square. Pi is 5, so it is pi 5 square. Here we have pi in the numerator and pi in the denominator, so pi will get cancelled. Here we will open the bracket. 5 square is 25, so it is 25 pi over 2 minus 2 theta times 25 over 2. So we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. So the area of sector DOL equals to 12 over 2 is 12.5. So this expression equals in total to 12.5 pi minus 25 theta. But we have already found out that theta equals to minus 1 of 0.5, so it is, and we have to subtract from it also the area of triangle DOL. So it is minus the area of triangle DOL, it is 5 times 5 times sinus pi minus 2 theta over 2. Okay. So the area of the lower circular segment DL of the big lens equals to 12.5 pi minus 25 theta, and theta equals to tangents minus 1 of 0.5 minus 5 times 5 is 25 over 2, and sinus pi minus 2 theta equals to sinus 2 theta. In conclusion, we found out that the area of the lower circular segment DL of the big lens equals to 12.5 pi minus 25 times minus 1 of 0.5 minus 25, here it is over 2, 25 over 2 times sinus 2 theta, and we have already found out that sinus 2 theta equals to 4/5, so we will substitute sinus 2 theta by 4/5, and we get that the area of the lower circular segment of the big lens equals to 12.5 pi minus 25 times tangents minus 1 of 0.5. Here we have 25 over 5 is 5, and 4 over 2 is 2, and 5 times 2 is 10. In conclusion, we found out that the area of the lower circular segment DL is equal to 12.5 pi minus 25 times tangents minus 1 of 0.5 minus 10. Now we know that the area of the big lens equals to the area of the upper circular segment plus the area of the lower circular segment of the big lens. So I write it down that the area of the big lens equals to the area of the upper circular segment of the big lens plus the area of the lower circular segment of the big lens. And we have already found out that the area of the upper circular segment of the big lens equals to (100 times tangents minus 1 of 0.5 minus 40, while the area of the lower circular segment of the big lens equals to (12.5 pi minus 25 times tangents minus 1 of 0.5 minus 10. So in conclusion, we found out that the area of the big lens equals to, here we have 100 times tangents minus 1 of 0.5 minus 25 times tangents minus 1 of 0.5 is 75 times tangents minus 1 of 0.5 we have here minus 40 plus minus 10 is minus 50 plus 12.5 pi. Okay, this is the area of the big lens, and we have already found out that the area of the blue lens equals to 12.5 pi minus 25, and we know that the area of the orange shape is equal to the area of the big lens minus the area of the blue lens. I'll repeat again. The area of the orange shape equals to the area of the big lens minus the area of the blue lens. Okay, and we have already found out that the area of the big lens equals to 75 times tangents minus 1 of 0.5 minus 50 plus 12.5 pi, and we have to subtract from it the area of the blue lens, that is equal to 12.5 pi minus 25. So we will open the brackets here, and we get that the area of the orange shape equals to 75 times tangents minus 1 of 0.5 minus 50 plus 12.5 pi, So we'll open the brackets here and we'll get here, it is minus 12.5 pi, minus is plus, so it is minus 25 is plus 25. So here we found out that we have here 12.5 pi minus 12.5 pi is 0, and minus 50 plus 25 is minus 25. So in conclusion, we found out that the area of the orange shape equals to 75 times tangent minus 1 of 0.5 minus 25. And we also know that the value of tangent minus 1 of 0.5 is equals to 0.4636. So we substitute tangent minus 1 of 0.5 by 0.4636 and we get that the area of the orange shape equals to 75 times tangent minus 1 of 0.5, and tangent minus 1 of 0.5 is 0.4636 minus 25. 75 times 0.4636 is 34.77 minus 25, and 34.77 minus 25 is 9.77 square units. So in conclusion, I found out that the area of the the area of the orange shape, according to the second method, it is equal to 9.77 square units. Okay. So the area of this green shape, according to the second method, equals to the area of this orange shape, according to the second method, equals to 9.77 square units. So in the next step, I'll summarize the lecture. We'll start with the first method. So in the first method, we developed a formula for the area of two shapes that intersect with each other and create at 90 degrees. They are perpendicular to each other and create in this way the length. And we use the formula in order to find out the area of the blue length. We use the same formula in order to find out the area of the big length, and we subtract the two areas from each other. And the result, it is of course the area of the the area of the orange shape. Okay. While in the second method, we directly calculated the area of the blue length, we directly calculated the area of the big length, and we subtracted the two areas together, and this gave us the area of the orange shape. Okay, so here we have so in the drawing we have square ABCD. We know that inside each side of square ABCD equals to 10 units. Inside square ABCD we have semicircle APD, and the other semicircle is CPD. They intersect with each other at 90 degrees, and this way they created the blue lens. In addition, we have the quarter circle ABE, DQ that intersects with this semicircle CPD at 90 degrees, and they create by the common area that is the big lens, this big lens. I'll remind you that a lens is the common area that was created by the intersection of two shapes with each other. So here we have the blue lens and the big lens, and our mission is to find out the area of this orange shape. Okay, so in the first method we created general formula for two shapes that are perpendicular to each other and they intersect with each other at 90 degrees, and in this way they create the lens. And the formula that we created is good in order to find out the area of the blue lens. Why? Because the blue lens was created by the intersection of those two semicircles that are perpendicular to each other, while the big lens was created by the intersection of the quarter circle with this semicircle at 90 degrees. Okay, therefore the formula that we created is good for the big lens and also for the blue lens. Why? Because those two semicircles are perpendicular to each other. This again equals 90 degrees. So we can use the formula to find out the area of the big lens and the area of the blue lens. So here we know that the radius of this semicircle equals to A units in its length, while the radius of this semicircle equals to B units in its length. And here we will find out the area of the green circular segment. We find out the area of the lower circular segment in the orange color. We'll add the two areas together, and this will give us a formula for the area of a lens that was created by two shapes that are perpendicular to each other. For that reason, we can use the formula in order to find out the area of the big lens that was created by two semicircles that are perpendicular to each other, and we also find out the area of the big lens that was created by the quarter circle that is perpendicular to the semicircle. Okay, why we can use the formula to find the two lenses? Because of the fact that those two semicircles are perpendicular to each other. This again equals to 90 degrees. Okay, so if A equals to 10 units, then this semicircle will actually become a quarter circle. Okay, and this will give us the area of the big lens. While if A equals to B equals to 5 units, then this will give us the area of the blue lens. Okay, but before that, I clarify two concepts. What is the area of sector? The shape in the green color, it is equal to the angle between its legs, that is theta, over 2 pi, that is the size of the angle of the whole circle. 2 pi radians is 360 degrees. So that ratio between the angles gives us the relative percentage that the sector occupies out of the area of the entire circle. And when we will multiply that presented by the area of the entire circle, it will give us exactly the area of this sector. So theta over 2 pi times pi r squared, that is the area of this circle, will give us exactly the area of this great sector. Okay, this is the first concept, and a second concept that will clarify here, that is the area of this great circular segment AB. What is the area of circular segment AB? It is very simple. It is equal to the area of sector AOB minus the area of triangle AOB. It is very easy to see that if you subtract the area of triangle AOB from the area of the sector AOB, will get exactly the area of circular segment AB, the shape in this green color. Okay. Then, so in the first step, we calculated the area of the upper circular segment MN and NL, but I remind you that the general formula for the area of this orange shape equals to the area of the big lens minus the area of the blue lens. The area of the big lens minus the area of the blue lens gives us exactly the area of this orange shape. Okay, this is the formula that we will use in both methods. So in the first method, first of all, we'll find out the area of the upper circular segment. The area of the upper circular segment NL equals to the area of sector NOL minus the area of triangle NOL. Again, the area of sector NOL minus the area of triangle NOL equals to the area of circular segment NL. Okay? So here, the area of sector NOL equals to theta A squared, and we have to subtract from it the area of triangle NOL, but we calculate the area of triangle. Actually, we don't need to calculate the area of triangle NOL because we combine this triangle with the other triangle and we get the area in another way, the area of the two triangles. So, in conclusion, the area of the upper circular segment of the area of the upper circular segment of this lens equals to theta A squared minus the area of triangle NOL. In the next step, we calculated the area of this lower circular segment. It is equal to the area of sector NML minus the area of triangle NML. Again, the area of sector NML minus the area of triangle NML gives us exactly the area of lower circular segment NL. I repeat again that the area of the lower circular segment NL in the orange color equals to the area of sector NML minus the area of triangle NML. Okay, so the area of sector NML equals to pi b squared over 2 minus theta b squared minus the area of triangle NML. So we have to subtract the areas of the two triangles from the sum of the areas of the two sectors. Here. In conclusion, if we add the two areas together, we get that the two areas together, that is actually the area of the lens that we are looking for, equals to the area of the two sectors, the sum of the two areas, the upper circular segment and the lower circular segment, equals to the sum of the areas of the two. First of all, the area of the green circular segment equals to the area of sector NOL minus the area of triangle element, plus the area of the lower circular segment, that is equal to area of sector ML, minus the area of triangle MNL. Okay? So here, it is actually equals to the sum of the areas of the two sectors, you can see it, minus the sum of the areas of the two triangles. Okay? And we already found out that the sum of the areas of the two sectors equals to this expression. Now our mission is to find out the sum of the areas of those two triangles, and then we will subtract that sum from this expression. Actually, in order to find out the sum of the areas of the two triangles, we combined the two triangles together, and in this way we created those two right triangles. The area of each right triangle is a times b over 2, so the sum of the areas of those two triangles is a times b. So now we have to subtract from this expression a times b, and this will be the area of this length. Okay? So the area of this length, that could be the blue length or either the big length, equals to this expression, that is actually the sum of the areas of the two sectors minus the sum of the areas of the two triangles. Here we took theta as a common factor, and in conclusion we found out that the formula for the area of the blue length and the area of the big length equals to this expression. We use this formula in order to find out the area of the big length. In the big length, the radius of the quarter circle A equals to 10 units, and the radius of the semicircle equals to 5 units. So we put the data inside this formula. A equals to 5, A equals to 10, and B equals to 5, and we found out that the area of the big length equals to this expression. Then, in order to find out the area of the big length, that the area of the blue length that was created by the intersection of the two semicircles with each other, that is to say A equals to B equals to 5. We put the value of A and B here, and we found out that the area of the blue length equals to 12.5 pi minus 25. And we know that the area of the orange shape equals to the area of the big length minus the area of the blue length. The area of the blue shape equals to the area of the big length minus the area of the blue length. We found out the area of the big length. We found out the area of the blue length. We subtracted the two areas from each other, and we found out that the area of this green shape equals to 9.77 according to the first method. Then I presented to you the second method. In the second method, we calculated directly the area of the blue length, then we calculated directly the area of the big length. We subtracted the two areas from each other, and the result is, of course, the area of this orange shape. So here, in the first step, we calculated the area of the blue length. We know that the radius of each semicircle equals to 5 units. So here, all the sides here are equal to 5 units, and because of the fact that the two semicircles are identical, it means that if we draw the radius that is perpendicular to the diameter, then it will also be tangent to this semicircle at point L. The same thing is true here. If this radius is perpendicular to the diameter, then it it will be also tangent to the other semicircle point L. So we have here square, and actually the area of this circular segment equals to the area of the quarter circle NOL, that is the area of the circle over 4. That is the area of sector NOL, that is actually a quarter circle, and if we subtract from the area of sector NOL the area of the right triangle NOL, it will give us exactly the area of this circular segment NL. Okay, so we found out that the area of circular segment equals to this expression. We multiplied by 2 and we found out the area of the blue lens, that is equals to 12.5 pi minus 25 square units. So we finished with the blue lens, then we found out the area of the big lens. We found out the area of the big lens. Here, first of all, we found out the area of the upper circular segment of the big lens. It is the same principle that the area of sector ADL minus the area of triangle ADL equals to the area of this circular segment. Then we found out the area of the lower circular segment NL. The area of this lower circular segment NL, according to the same principle, is equal to the area of sector LOD minus the area of triangle LOD. Okay, repeat again, it is equal to the area of sector LOD minus the area of triangle LOD. Then we added the two areas together, and this gave us the area of the big lens. This is the area of the big lens. That is the sum of the areas of the upper circular segment and the lower circular segment. We already found out that the area of the blue lens equals to 12.5 pi minus 25. And we subtracted, so the area of the orange shape equals to the area of the big lens minus the area of the blue lens. We have already found out that the area of the big lens equals to this expression, the area of the blue lens equals to this expression. We subtracted the two expressions from each other, and the result is the area of the orange shape, that is equal to 9.77 square units. So in both methods, we found out that the area of this orange shape equals to 9.77 square units. Okay, so in the first method we actually created a general formula for the area of the blue lens and the area of the big lens, and we subtracted the two areas from each other, and the result is the area of this orange shape. While in the second method we directly calculated the area of this blue lens. We directly calculated the area of this big lens, and we subtracted the areas from each other, and the result is the area of this green orange shape, that is equal to 9.77 square units. So we arrived to the same result in both methods. Okay, thank you very much.